Hello, this is the second video on applications of linear systems. Again, we'll get a linear system out of non-mathematical problems. So this time it will be balancing a chemical equation. So imagine we have a chemical equation given to us, namely some collection of compounds like potassium ferrocyanide reacting with sulfuric acid, diluted, gives something else, gives a mixture of potassium sulfate, iron sulfate for 2-lanthanum, and I'll have to move it to the next line, ammonium sulfate, and some amount of CO. And the task is to find the proportions. So we have as many unknowns as the compounds in the reaction as the agents. So that is X1, that many molecules, and then X2, X3, X4, X5, X6, and X7. So we have 7 variables. And the balancing will go through each of the chemical elements involved in those compounds and those reagents, and we will have as many as elements. So for most of the elements, the equations will be rather easy. And so this menacing task of solving a system with 7 unknowns and 1, 2, 3, 4, 5, 6, 7 equations will be actually not that bad. So let's start looking at balance. And yes, for certain elements like potassium, like iron, like carbon, there is just one reagent on the left and one reagent on the right containing each of those elements. So we will have a perfect equation with one variable being expressed through the other. So let's start looking at elements in order of their appearance and then the corresponding equations. So potassium is in here, and it's 4 atoms in each compound. If we have X1 number of those molecules, we'll have that many potassium atoms on one side. On the other side, we have 2X4. For iron, we have just X1 matching with X5. For carbon, we have 6, X1 on one side and then X7 on the other. For nitrogen, again 6, X1 has to match with the amount of nitrogen in this ammonium sulfate, which is 2, X6. So these are all basically answers for the variables on the right-hand side of the chemical equation in terms of X1. We could think of X1 as our first free variable, which is sort of unconventional. Traditionally, we have X1 serving as a pivot. But yeah, it sort of makes sense in the way the the chemical equation of the system is written. But yeah, let's continue collecting equations. for other elements. For hydrogen, we have 2x2 and then 2x3, because both of these compounds contain hydrogen, matching with the hydrogen on the right, which is only in the ammonium sulfate, and that is 8x6. For sulfur, we have x2 on the left, and this time we have many variables on the right, x4, x5 and x6. Each of the corresponding compounds have just one atom of sulfur. Finally, oxygen. For oxygen, we have 4x2 and then 1x3 on the left, matching with 4x4, 4x5, 4x6, and then one copy of x7. So that is the system as it is coming from the chemical reaction. We have 7 unknowns, 7 equations, but these equations are very easy. So these equations are effectively answers for our unknowns on the right of the chemical reaction in terms of x1. Let's use these answers to write the right-hand side of these remaining equations as quantities in terms of x1 only. So here we have 8 copies of x6. X6, 2 copies of x6 is 6 copies of x1, which is really saying that x6 is 3 times x1. So we have 3 times 8, we have 24 x1 here. So here we have the sum of x4, x5, and x6. So x4 is 2 copies of x1, x5 is just 1 copy of x1, x6 is, as we computed before, 3 copies of x1, so total will be 5 times x1. Just check that everything is in order. Yeah. And continuing with, it's not really, it's 6. Arithmetic is difficult. And now doing it here, so we have, again, the sum of x4, x5, x6, but now 4 times, and then a copy of x7, which is 6, x1. So the sum of just x4, x5, x6, the sum is 6 times x1. We have 4, so we have 24 x1, and then for x7 the answer is in here, 6 x1, totaling 30 x1. And I will be just solving the system of these 3 remaining equations for the unknowns x1, x2, x3. And then the answers for other will be are determined by this. So that will be a simple task. Just writing these equations, maybe I can squeeze it in here. What I have is 24 x1 minus 2 copies of x2 minus 2 copies of x3 being 0. And for this equation, I have 6 copies of x1 minus x2 being 0. And for this equation, I have 30 x1 minus 4x2 minus x3 being 0. So that is the system in the more canonical form, and that is a homogeneous system. Whenever we balance quantities of compounds in a chemical equation, we always will have a homogeneous system. So we'll always have a trivial solution where all amounts are 0. And that is a really bad balance. That is really saying that we don't do this chemical reaction at all, because we don't have any compounds reacting. What is interesting is having a non-trivial solution, and for that case the system should have free variables, because if all the variables are pivots, the only solution we will have is all zeros. So we need to have a free variable for that equation, that chemical equation, to balance out. Let's see if we do. Let's write the matrix of this system, and this time it will be a non-extended matrix because the system is homogeneous. Now x3 in the second equation, and in the last I have all present, and that is the equation. And what the setup is suggesting that we should treat x1 as a free variable. So if x1 is a free variable, then we should express the rest, if possible, as functions of x1. And we actually can, because we have sort of two pivots sitting in the system, potential pivots for x2 and x3. So we could really use them to pivot the system around them, and then write the row echelon form and then reduced row echelon form in terms of them. So I will be using this first. It will be looking unconventional. It will be sort of looking weird in terms of standard Gauss elimination process, but it is really not. We just use different columns. We're starting with this first column, and we're creating pivot in here, and then we continue with the second column, and so on. So that is the only unconventional bit in what I'm going to do. And I'm going to really use this as my first pivot and eliminate this number in it. And yeah, it's sort of easy. I can do it in yeah, maybe before that I can do something again unconventional. I can eliminate this 4 from my first pivot equation, so I will have just pivots sitting on their own. So that will be done by row addition, row 3, without 4 copies of row 2. The first is unchanged. And then second is also unchanged, and I'll have 0 here. I will not change my first pivot in here, and then I will be subtracting from 30 4 copies of 6, so 24. I'll have 6 left. Now I have just pivots isolated in the equations and then as a free variable, so that is already the signal that if the system is compatible, we will have x1 as the only pivot. All I need to do now is to eliminate, make zeros in here, eliminate these non-zero numbers in the pivotal columns, number 2 and 3. So that I can do in, again, one transformation, row 1 minus 2, row 2 minus 2, row 3. These pivots are now independent. They are surrounded by zeros, so I can eliminate numbers in their columns at the same time. The pivotal rows are not changing. Then I'll have 0 and 0, and what I'll have in the first position of the first column, of the first row, is 24 without twice this and without twice this again. So that is again perfect 0, and it means that my system will have a one-parameter solution. It will have a solution expressible in terms of x1 only. So what the equations are now saying, that 6 copies of x1 minus x2 is 0, which is the same as to say that these are the same, and the same for the third equation, 6x1 is x3. So x2 and x3 are just 6 times x1, and adding it to the first bunch of equations, again here we just have the answer 2x1 equals x4, and here we have the answer 3x1 equals x6. So we have answers for all the compounds in the equation. If we set x1 to be, say, the smallest reasonable quantity like 1, we will have this balance. One molecule of potassium ferrocyanide. X2 is going to be 6. So 6 of sulfuric acid. X3 is also 6 molecules of water. X4 is twice X1. X5 is just X1. X6 is 3 copies of X1. And the carbon monoxide appears in, again, 6, proportion 6 to X1. So that is the balance of this equation. There is only effectively one balance because there is only one parameter family with a parameter x1, one parameter family of solutions, and this extra parameter is just how many times we take this equation total. But the balance inside the equation is after that unique. Let me solve this this matrix, this system in the canonical way. Let me do it again, just to use it as an example where we can do in every example we can solve in many ways, but let's now do it in the standard Gauss elimination way. I will still be slightly non-standard. According to the standard Gauss elimination way, I should create my first pivot. I should put it in the pivotal position here if I can, and I should eliminate its column. And for that, I should make it 1, scale down to 1. But that's what I will not do. I will use this 6 as my first pivot. So placing it in the right position, I will do the row swap between first and second rows. And it's still good for elimination purposes because all other numbers are divisible by 6. Good in the sense that I will not need to use fractions, which is always good. Eliminates 24 below my first pivot here. I will have to subtract 4 copies of first row from the second. And to eliminate 30, row 3 minus 5 copies of row 1 is the right transformation. The first row is not changed. And I'll have zeros. In here, I need to compute -2 minus 4 copies of -1. So adding 4 to -2, it gives me 2. Then I have -2 again here. And in this position, I need to again subtract 5 copies to -1 from -4. So adding 5 to -4 gives 1, and -1 here. And that is it for the first column. So I'll keep my first pivot as 6. And then progress into the next column. Again, I need to choose my first pivot, and whatever I choose, I can scale this down by 2 or swap the rows to make 1 sit in here. So say swapping again, row 2, row 3 will be my choice. And then I have my 2 pivots. So this is the first pivot, this is the second pivot. Need to eliminate 2. row 3 minus 2 row 2. And it happens that these rows are proportional, so when I eliminate, I actually eliminate the whole row 3. And that is a row echelon form canonically. And then I need to do one more elimination to make it a reduced row echelon form. To reduce it, I need to get rid of this -1, make it 0, because it is in the second pivotal column. So that will be done with transformation row 1 plus row 2. 6, 0, -1, 0, 1, -1, and I will not write the last 0 column. 0 row rather. So that is it. That is the reduced row echelon form. Maybe just one more push to make it all canonical, to divide by 6. So 1/6 row 1 will be the last transformation, which will make it look like that. So now that is the canonical sort of shape of reduced row echelon form. We have our two pivots. This time the pivots are the x1 and x2 variables. And then x3 is the free variable. And then the answer will be x1 minus 1/6 x3 equals 0, or them being the same. And the second equation is x2 being x3. But yeah, this is what we should have seen as a canonical output of the system here. But that's the same information. Again, it says that x3 is 6 copies of x1. Sorry, that is, yeah, x3 is 6 copies of x1, and x2 is equal to x3, again, 6 copies of x1. So this canonical way makes us use x3 variable as our free variable for the whole thing. But yeah, it gives us the same outcome anyway. So this is a good illustration of how different the answers could look if we are solving it differently, but the set of solutions will be the same. That is it. See you later.